Let's look at an example of an application involving law of sines. So in this example, we're told that we have two tracking stations that are being used to record the angles of elevation of a rocket after it's launched. And during one rocket launch, we have station A, which recorded the rocket with an angle of elevation of 30 degrees, and at the same time, station B recorded an angle of elevation of 80 degrees. Okay, so we have these two um, recording stations, tracking stations A and B. They've recorded the rocket at the same time at two different angles of elevation. Both stations are due east of the rocket, so we're just assuming this is all kind of level ground. We're not told anything else. And we're also told station A is 4 miles east of station B. So they're both east of the rocket, but A is further east than B. Okay, so what we want to find, there's two parts that we want to find. First, we want to find how far is the rocket from each station at that point where they're recording these angle of elevations. And then we also want to find what is the altitude of the rocket at the same time. Okay, so with all of these problems, let's start by drawing a picture. Okay, so the idea here is we have a rocket that is taking off. So it's going to kind of be going straight up. So that's our rocket. And along the ground, we have these two tracking stations. So these two tracking stations, we know A is the furthest east. So A is all the way to the right, and B is kind of in the middle, somewhere between the rocket and station A. And we know that they are 4 miles apart. So the distance from B to A is 4 miles. Okay. We are then told the angle of elevation for each. So from point A to the rocket, we are told that has an angle of elevation of 30 degrees. And then we're told from point B, the angle of elevation is now 80 degrees. Okay. So when we look at our picture here, and that's all the information that we're given, when we look at this picture, there's actually sort of three triangles that you should see here. Okay. There is the big triangle, which has the vertical side for the rockets taking off, the entire bottom side, which goes from the right angle in the bottom left corner all the way over to angle A, and then you have the hypotenuse, so that's the big triangle. You have the smaller right triangle, which again goes from the rocket on the far left, and then the acute angle along the bottom is B, so that's our 80 degree, and then the hypotenuse is the diagonal line. And then you kind of have this obtuse triangle that goes from point A to point B and then up to the rocket. Okay, so we kind of have these three triangles in here. What we are wanting to find is the length of, for the first part, is the length of the two diagonal lines, the sides of the two diagonal sides here. So let's just call them X and Y. You can use whatever letters you want. It doesn't really matter. So R is the angle up where the rocket's located. We may not need that, but we might. We'll see. So let's take a look at the information that we're given. We have a 30-degree angle. And right now we're looking at this, the obtuse triangle. I have a 30-degree angle, and I know the bottom side is 4 miles. That's the only information I know about this obtuse triangle. The actual information that we know. We can find more, but that's all we know is we know one angle and one side. Okay. So right now, it may not even feel like we're looking at a law of sines problem, but we can take a little step further here at angle B, at point B. We know we have these two angles here. One of them is 80 degrees, and the other angle is the obtuse angle inside the triangle that we're working with. Okay, and since they are both along a straight line, we know they have to add up to 180. So that means angle B inside our obtuse triangle has to be 100 degrees. Again, just because the two of those are supplementary, they have to add up to 180 degrees. So that means I now have two angles and the side between them. And so that would become an angle side angle problem. Okay. And so we need to find the length of our two sides. But to find side X, that pairs with angle B of 100 degrees. To find side Y, that goes with angle A, but none of those really have a known side. And so that's where the 4 miles comes in. This 4 miles is opposite angle R. So I need to know one of my whole ratios. And right now, the ratios that I'm looking at would be the sine of 30 degrees over, what's the side opposite 30 degrees, over Y. If we look at sine of 100 degrees, that is over X. And then we have the sine of R over 4 miles. So again, right now, none of my fractions has both values known. That each have one known and one unknown. So I need to find R next. Okay, and again, that's not hard. We know that the sum of the three angles have to be 180 degrees. So A plus B plus the R angle has to be 180 degrees. And we already know A is 30 and B is 100. So 30 plus 100 degrees plus R has to be 180. So if we subtract that and solve for R, we will get R is 180 minus 130, which is 50 degrees. So we know R up here is 50 degrees. That's that little acute angle inside the obtuse triangle. Just to make sure, we have 100 plus 30 plus 50 is 180. So our angles add up. And so now I can go ahead and replace the R in my proportion with a 50 degree. And I now have one ratio that has both of the values. And so I can go ahead and set those up to figure out the two unknown sides. So if we take this, let's do X first. So if we take the sine of 100 degrees over X, that has to equal the sine of 50 degrees over 4. We can then cross multiply and divide in order to solve for X. So if we cross multiply and divide, we will get X times the sine of 50 degrees is equal to 4 times the sine of 100 degrees. We divide the 50, or the sine of 50 degrees, to both sides. So X is going to equal 4 times the sine of 100 degrees over the sine of 50 degrees. And we can compute that on our calculator. We're going to get that X is equal to 5.14 miles. Okay, so that's the distance from the rocket to tracking station A. To find the distance for tracking station B, that's the Y value. So we're going to set up the proportion sine of 30 degrees over Y is equal to the sine of 50 degrees over 4. We cross multiply and divide. It's the same algebra, just different numbers. So it's going to end up being Y equals 4 times the sine of 30 degrees over the sine of 50 degrees. And if we compute that on our calculator, we will get that Y is equal to 2.1 miles. Okay, so those are the distances that tell us how far the rocket was from each station. Okay. The second part of the question is we want to know what is the altitude of the rocket? What is its height? Okay. In our illustration that we started with, that is the length of that vertical side. Okay. And if we look at that, that is actually part of a right triangle. That's the smaller right triangle. So let me break that apart and look at that smaller right triangle here. So for this right triangle, we know we have our right angle. We know the bottom acute angle is 80 degrees because that's where B was. That's at point B here. We know the side opposite, B, that's the vertical side, that's H. And we just found the length of the hypotenuse. It's the Y value. We just found that to be 2.61 miles. So if we are looking at angle B, which is 80 degrees, we are working with the opposite and the hypotenuse. That's just sine. Okay, so that means we're looking at the sine of 80 degrees, and that has to equal H over 2.61, which means H is going to be 2.61 times the sine of 80 degrees, which results in an H, a height of 2.57 miles. So we now know how high, what is the altitude of the rocket at that point in time. It's 2.57 miles high.